So I want us to talk today about stable or locally jammed configurations of disks. And this is an example here of a stable configuration of 5 disks. And we say it's stable because no disk can move. And mathematically, it's very easy to check that no disk can move because each disk individually is held in either by its neighbors or by the sides of the square. So that's the definition of stable, or in the physics literature they call it locally jammed, is that each disk is held in place by its neighbors or by the boundary of the region, if there is a boundary. And that's something that you can check easily, just sort of locally, just at one disk at a time. Look at the tangency directions, and then if any of these angles is more than pi, then the configuration would not be stable. But if all these angles are less than 180 degrees, then configuration would be said to be stable. So we'll construct a stable configuration of disks in the plane that's very well known and that was conjectured to be the sparsest such configuration of disks in the plane. So it's well known that the plane can be tiled by regular 12-gons and equilateral triangles, and here's a picture of that, a so-called Archimedean tiling. So if we put a disk at the every vertex in that tiling of regular 12-gons and equilateral triangles, then we get a stable configuration of disks in the plane. This is an infinite configuration of disks, and the great geometer Laszlo Fejes-Tóth conjectured that this was the sparsest configuration of stable configuration of disks in the plane. This is the same Fejes-Tóth who proved that the honeycomb lattice is the densest packing of disks in the plane. So this was his question: is this sort of the sparsest configuration that you could have? So now I want to describe the counterexample to the conjecture that that configuration we just saw really is the sparsest stable configuration. A very surprising, delicate counterexample of Brodsky. So Brodsky builds a bridge here. So he starts with 5 disks along, sort of situated along the y-axis, and then the construction can be described sort of one disk at a time. There's a convex curve here through these disks along the top row. And it's very slowly decreasing curve, and maybe it's asymptotic to a horizontal line. And so the angle at the disk A between any of its two neighbors is just less than pi. So then once the A's are in place, then we can put in disk B2 so that it's tangent to A2 and C1. And then we can put in C2 so that it's along the x-axis and tangent to B2. And simultaneously, we're doing the same construction on the other side of the x-axis in a completely symmetric way. So then once disk C2 is in place, we can put in disk B3 so that it's tangent to A3 and C2. And then we can put this C3 in place and then B4 in place, and so on. And in this way, we get a configuration of disks that's stable almost everywhere. So this picture actually continues forever to the right. This curve at the top here is very, very slowly decreasing. And every disk here is stable, is held in place by its neighbor, and the only exception is the shaded disks on the left. So Brodsky's bridge is almost a stable configuration disks on its own, but except at that end, the left end we saw on the last slide. So he needs a way to fix it at the end. And so here is his beautiful idea. He puts together 3 of these bridges, and then he has them meet together at this center junction. So here's a picture of Brodsky's construction. We see 3 bridges, each going off to infinity in a different direction, and then they meet at this junction in the middle. So this is essentially a one-dimensional construction. It's it's sort of got thickness, but if you back up and looked at this from a bird's eye view, these bridges would get thinner and thinner and thinner. And so, since it's essentially one-dimensional, we would say that this has zero density in the plane. If you measure the area of these small disks, the total area in all the small disks, divided by the area in a very large disk, as the large disk gets bigger and bigger, the ratio goes to zero. So a question I was interested in a few years ago is asking how small a stable configuration of disks can be, but instead of in the plane, inside a square. So we're looking at this picture again. This is 5 disks in a square, and this is a stable configuration. No disk can move. But we could measure the total area of the disks in this, and then we could ask, well, how small can we make that? If we're allowed more and more disks, they've all got to be the same size. How small can we make the total area and still have a stable configuration? So perhaps surprisingly, the answer is we can make the area arbitrarily small. So inspired by Borodski's configuration, the first thing we need to make is a new bridge. So we follow Borodski's construction, except now instead of a convex curve that's extending out to infinity, we have a line of symmetry, and so the curve is only decreasing up until a certain point, and then it continues increasing from that point on. So the curve through the centers of these disks is maybe always concave up. So this is a symmetric adaptation of Borodski's bridge. But we need a way to put those bridges together so that they fit in the square. So here's a junction piece, and you can see that the 5 squares on the top and also the 5 squares on the right, those are actually the exact angles that you need to be one end of one of those symmetric Brodsky bridges. But it turns out that these disks can be arranged geometrically so that these fit along 2 sides of the square, and then that you can put the bridges along the right side and the top. So now we have a symmetric version of Brodsky's bridge, but we need a way to put them together. So this is a corner junction piece that will allow us to do that. And the top disks and the right-hand 5 disks will allow for Brodsky bridges to be placed, and those 2 bridges will intersect just at a corner here. So once we put the corner junction pieces together with the symmetric Brodsky bridges, then we can actually make a stable configuration in the square. So the point is that these symmetric Brodsky bridges can be made as long as you like, so that in the end we can make the density of these configurations arbitrarily small. So just as Borodski's original counterexample in the plane is something that's zero density in the plane, here we can't quite get zero area for the stable configuration in the square, but we can get arbitrarily close to zero by taking a sequence like this. And we've just seen the first 2 in an infinite sequence where these bridges get longer and longer and the disks get smaller and smaller. So in the limit, the area is going to 0. So there's a lot of connections of this work, and what this was originally inspired by is some problems in physics. This related to hard spheres gas and phase transitions in physics. And geometrically, this to me looks like a very simple model of matter, and what we're seeing here is something like ice forming inside a window, but it's a sheet of ice that's only maybe 5 atoms thick. But maybe I can tell you about liquid-solid phase transitions in hard spheres gas in another talk at some point in the future.